So power functions, this is pretty straightforward. There's a lot of language in the assignment for today. You're going to be writing down a bunch of words, which is kind of strange. Or you'll be reading sentences and translating them into equations. But other than that, this is mostly an exercise in like looking at an equation, and if it doesn't look like it's in the right form, changing your notation to make it fit into the right form. So we want to be looking at equations that look like this today. But some of them aren't going to look like this. They're going to have square roots. But we know how to write square roots as exponents, right? You're thinking of division, which we will also do. How do we write a square root as an exponent? You remember? Like the square root of x is the same as x to what power? 1/2. And the cube root of x is x to the 1/3 power. Does that sound familiar? Yeah. So that's going to come up a bunch. And then other than that, really, we're just practicing chapter 1 stuff. I warned you the stuff that we were doing in chapter 1 is going to come up again and again and again. Every time we look at a new function, we're going to go back and do that analysis piece. We're going to look at domain and range and continuity and boundedness and intercepts and asymptotes, all that fun stuff. I've got a nice little list we'll copy down here in a second. So that's a preview of what we're getting into today. Let's go ahead and get after this. I'm going to give you a couple examples and we'll work through together. So everybody got that first piece down? No, I took it away too quick. I'm sorry. So power functions are going to be in this format. You've got some constant variation. They use K in our book. I will just refer to this as the constant. I'm not going to write down constant of variation each time. I'll just write const. And then you got a power. It's important that the power is the thing on the x and not the other way around, because then you're not looking at a power function. You're looking at an exponential function, which is chapter 3. We'll get there. Power functions for today, though. All right, I'm going to move on here, and if you don't have everything down, just leave some space. We'll come back to it. A couple examples for you here. And again, we are going to be writing some words out here, so let's feel a little bit like English class. A equals I r squared. I would make the claim that this is a power function. What do you think? You agree? Kind of looks like it's in that form. If it were a power function, what would the power be? Power is 2. And the constant of variation, in this case, would be pi. We're going to translate this into words. A portion of your homework is going to be kind of the reverse of this. They'll give you the words and you're going to write the equations. So we'll practice that a little bit too. All right, a couple of ways we can do this. I would start this off as A. We know what this formula is, right? A stands for what? Area of a. So the area, and then there's 2 ways that we can do this. The book uses these interchangeably. Either is proportional to, or varies as. The square of the radius. The area is proportional to the square of the radius, or the area varies as the square of the radius. Both mean the same thing. I had to write it out. I would probably write it separately. reminds me. You know why we spell color C-O-L-O-R in the United States, but in Britain they spell it C-O-L-O-U-R? So it's a American thing. We used to spell it that way too. We started dropping letters out of stuff. And the reason was when the printing press came along, and we wanted to put an advertisement in the paper, you paid by the letters. So people started strategically removing letters from words that they didn't really think needed to be there. You can still convey an idea. It's just an advertisement, right? So no big deal. And then people got used to reading it that way, and then they stopped putting it in everything. So it's out of trying to save a couple cents. The printing press. So varies as would be the cheaper way to go if you were trying to put this in an advertisement for some reason. All right, let's do another one. Let's stick with the theme of circles here. C equals, probably finish this one. For a circle, circumference equals. Thank you. That's a power function, isn't it? Kind of. I could rewrite that as 2 pi times r to the first power, couldn't I? That's a power function. Yeah. Power is 1. Constant of variation is 2 pi. So we could write a sentence for this one too. It would say the circumference. I'm going to go with varies as this time. Circumference varies as, and I wouldn't say the square of the radius this time. I would just say the radius. So the circumference varies as the radius. Or it could have said the circumference is proportional to the radius. It's pretty much just saying that, like, the circumference is good. Yes. Yep. So if the radius gets bigger, the circumference is going to get bigger. It's really saying if the radius gets twice as big, your circumference is going to be twice as big. If your radius grows by a factor of 5, your circumference is going to grow by a factor of 5. Area is different though. If your radius grows by a factor of 5, then your area is going to grow by the square of that by a factor of 25. All right, one more. 2 more. Actually, a whole bunch more. I don't know why I said that. We're not even close. So it looks familiar. No, good guess though. Fahrenheit to Kelvin. No, K is actually the constant in this case. D would be kind of like my X. It has to do with gravity, actually. So F is the force of gravity, and D is how far away from the center of the Earth you are. So further away you get, the less gravity you have, right? Closer to the center of the Earth, more gravity. That's what it means. But what we need to be able to recognize is that it is a power function. We could write it as K times D to what power? You know, it's the second, but it's on the bottom of the fraction, so negative. So you see what I mean when at the beginning I said you're going to have to take some equations and rewrite them and try and force them into a certain form. We're always trying to write it as some constant times some variable to a power. In this case, my power is negative. That's okay. You're allowed to have a negative power. You're allowed to have fractional powers too. And constant is K. Yep. I'm sorry. Irrational powers, yes. So our power function rules are that the power cannot be equal to 0. So it needs to be a real number, not equal to 0. So not imaginary. We won't get into imaginary powers just yet. Wait for semester 2 for that. All right, and if we want to try to set things, it would look something like this. The force is, okay, so this is a little bit different here. I'm going to write out both versions. The force either is inversely proportional to or varies inversely as. The square of the distance. So even though my power is -2, I'm still talking about the square of the distance. The thing that in words links it to the negative power is this word inversely. We throw that in there anytime we have a negative power. All right, one more. One more and then one more after that. So just like the last couple, I'm going to make an attempt to rewrite this in the correct form. We want x to be the base and then the variable to be like something on it. So what are we looking at here? What do you think? I like what you're thinking. We'll get to logs next unit. We won't see logs too much in this unit. Here's the question: is it a power function? It is not a power function. So for right now, we're just going to be satisfied to say it's not a power function. It's not a variable being raised to a power. The variable is the power. It is actually an exponential function, which we'll get to next unit. I know you guys can't wait. Those logs. Did you like logs last year? Logs are super useful. They're very useful. Oh, it'll be easier this year. Trust me. If you've already seen them once, then it'll be easier. Every time it gets a little bit easier. Okay, one more. Let me give you one that's going to look like your homework, so you can see why we're doing this. So in the homework, they're going to give you words, and you just have to write an equation. This is pretty straightforward. But let me give you an example, because my students are always a little intimidated by this at first. Here, you know what? I've already got this. Just cover up my answer. The speed p of a dropped object versus the square root of the distance traveled d. Use k as your constant. 55%. It's up to you. I'm providing it as an example of what it's going to look like in your homework. So this is what you'll see in your book. This is actually one of the even numbered problems. I only assign the odds. But this is one of the ones in that same section. And all your job to do is to write an equation. Your equation should have P and D and K in it, and then any other information you might need, such as power. And once you have that equation done, then that's you finished. So these are going to be pretty quick problems. There's no work really to show. So see if you can write me an equation that starts with P equals that has D and K in it, and that would match the description that we're seeing here. Now I do not see the word inversely in this anywhere. So I would not be thinking of writing a fraction with a power on the bottom of it. To see a square root, we talked about how we can write a square root as a power. Give it a try. Give it a try. And I'll show you what I think the answer is. A couple different ways you can write it. Do you write P equals? Yes. You put K out in front, and then after the K, you add a D to a power. Yes. And what power did you use for that square root? 1/2. Wonderful. That's what I wrote too. This would be just fine also. Let's see. Oh, that's supposed to say D, not P. Typo. I didn't scan this yet. Wonderful. So that's kind of like the new stuff. From here on, we're just going to do old stuff, but we're going to practice a little bit together today. So I'm going to work through one example, and I'm going to ask you to do a couple on your own. And then the rest of our time will be work time for homework. Anybody have any questions up to this point, though? A little bit of a lighter lesson, I would say, than some of the ones that we've had, right? Pretty simple. We got power functions, we've got a constant and a power. Sometimes we have to think about what the power looks like. We'll see them get a little bit trickier, but all right. So expectations from here on out. When you run across anything in your book, homework or otherwise, it asks you to analyze a function. That's the stuff that I want to see. So you're going to see in there's two problems in your homework. It says analyze the function as in example 2, and we're not going to do example 2. We'll leave that for you to read out of the book. If you need another one, we'll do a couple that are similar to it. But when it says analyze, I need to see all this stuff listed up. So all this stuff that we practiced in chapter 1, we're going to do that. Power functions today. We're going to do them with rational functions next week. In a month or so, we're going to do them with exponential functions and log functions. February, March, we'll be doing it with triple functions. Oh, by the way, while you're writing this down, I need to get this on the website. If you're interested in a retake on the chapter 1 test, just see me or email me. And we're going to need to schedule a time. If you're going to retake it, you will need to come in and sit down with me. We need to look over your original test. And there will be a retake practice assignment that I'll ask you to complete before doing the retake. So get in touch with me if you're interested in doing that. Keep in mind the retake, you can only do one, you can retake one test per semester. So we will have 3 chapter tests in our final exam. You can't retake the final exam though. And retake is for not a replacement, but I take the average of the 2. So if you scored a 60 the first time around, you score 100 the second time around, you end up with an 80. And yes, if you do worse on the retake, I will lower your grade. Don't do that. If you do the retake and you're feeling terrible about it, you will have the option to throw it away instead of turning it in to be graded. Okay. Do we need a moment here still? I'll leave it up for a couple more minutes here, and I'm going to write down the function we're going to do, and we'll get right after it. It's this. Oh, this is a good one. I got it frozen. Oh, what a beauty. So we're going to graph this. We're going to analyze it. Let's start our analysis by making sure this is indeed a power function. I can rewrite a cube root as a power of, so I could leave the x squared instead of a cube root. I could take that whole x squared to the power of 1/3. And I'm super hopeful that we recall our rules for exponents. What happens when I have an exponent on the inside and outside of parentheses? And multiply 2 times a third is 2/3. If you're super confident with how to deal with exponents, then logs are going to be nice and easy for you because it's the same rules. Logs are just exponents. And that looks like a power function to me. Power is 2/3 constant of variation. Great. And your instructions in your book are going to say graph. And you know what I expect when I say graph, right? On graph paper, accurate graphs with actual points plotted in the right places. So let's practice doing that. Draw ourselves a little XY axis here. Now, I will be honest with you, I'm not 100% sure I know what this looks like. 2/3 is less than 1. So I don't know. I think it's gonna kind of look like a square root-ish looking thing. But I also think it might be, it seems like it's going to be an even function. If I put negative x in for x, the square is going to cancel that out, right? So it should also be symmetrical about the y-axis. So I don't know, it's could look kind of wacky. Let's use our calculator. And I'm going to just type it in like this. That's easier. 2x to the 2 divided by 3. It does, but it's kind of curved. Yeah, it does. It kind of looks like a square root. That looks to me like a square root that's been kind of reflected across the y-axis. So let's get some points here. Remember, you got second graph. We'll get you some nice points. Let's at least get a handful of points in the right place here. Eyeball them anyways. 0, 0. That's predictable. 1, 2, 2, 3.2. They're kind of getting reflected over 3, 4-ish, over 4. That's good. All right, so when it says graph, I want to see a good graph. Nice points on it. Should look fairly accurate. If it says sketch, if this had said sketch instead, here's what my sketch would look like. That's good enough for me for a sketch, okay? So check those instructions. It says graph. Please make a good graph. All right, so there we are. Well, let's just start in on our list here. So let's talk about domain. I do not see any fractions. I don't see any even numbered roots. So I think the domain is going to be all real numbers. We don't have any of those things that have restrictions. So, and congratulations, you have graduated past chapter 1. If you would like to rate the double bar R instead of interval notation, I'm okay with that from here. So, domains, all real numbers. Range, doesn't seem like we're ever going to get any negatives out of this thing. So I'm going to say 0 to infinity is 0 is on the graph. So 0 gets a bracket. Stop me if at any point here you're unsure about any of this. What do we got next? Continuity. Is this graph continuous? Yeah, it is. There's no breaks in it any place. Local extrema. These would be local maxes or local mins. Let's see a local min. At the origin. What else is on here? Increasing, decreasing, constant. I see decreasing here and then increasing over here. So let's do those. Remember when we do increasing and decreasing, we do them as intervals. You have X values, not Y values. Symmetry? Yep. It's symmetric with respect to the y-axis. Which means it should be even or odd. Should be even. I would like you, when you're doing these problems, to practice your even and odd. If you think it's going to be one or the other, to do it algebraically, like I asked you to do on the test. It's going to come up again later, and I just want you to be really comfortable with it. So let's do that. We always start checking even and odd algebraically by writing f of negative x. And then take negative x and plug it in for x. And any one of these versions would be fine. I'm going to go with this one here. 2 times the cube root of parentheses negative x squared. And then simplify that. That negative is going to go away. It's just going to become x squared. Which, hey, that's the same as the original. So make sure you write this last piece. Equals f of x. The whole point of me asking you to do this is for you to start with f of negative x and link it to f of x, because that is the definition of even. What else we got on our little list here? Boundedness. Is this thing bounded above or bounded below or both? Definitely bounded below, but not above. Asymptotes. I don't think so. I think this is going to keep growing forever and ever. It's not going to level off to some specific value. There's no vertical asymptotes, so yeah, no asymptotes. And I got a little space here. Let's squeeze in our end behavior. We didn't have end behavior on our test, did we? That's all right. We're gonna see it on. It's always gonna look like that. Now let me give you a little hint here. This is talking about what's going on way off to the left and way off to the right. If this had just been a square root, if there was no way off to the left, we would write does not exist here. Okay, you're going to see that come up in one of the ones you're going to do in a second. Okay, so this time, though, it does exist. There is something going on way off to the left. And the question is, there's basically three options. Is it heading towards positive infinity, down towards negative infinity, or is it leveling off at a particular value? And I would say this is heading towards positive infinity on the left. So that's infinity, and that's heading to positive infinity on the right also. So that's also infinity. And that's analyzed. Doesn't that feel good? Woo! All that fun stuff from chapter 1 that we get to do again and again and again. And by the time we get to chapter 3, you'll have done this so many times it will just be second nature to you. Okay. So all we have left to do, I want you to practice this a little bit. I'm going to ask you to do a couple more functions for me. These are both power functions. I will be checking your homework off while you're working on that. Can you just go through and do what we did for that last set of functions for both of these? All that stuff from your list. Domain, range, continuity, schema, etc., etc. And I'll share my answers with you here in a minute. We can check and see how we did. Ask each other questions. Ask me questions as I'm coming around, but have your homework out so I can check you off for that. All right, can I get you guys to check on the first function? You should be done with one of them at this point at any rate. Were you able to rewrite this as 1/2 times x to the 3/2 power? Okay, so that we know that the power is 3/2 and the constant variation is 1/2. This problem does include a square root, so we would need to apply the restriction for square roots, which is anything inside the square root must be greater than or equal to 0. So x cubed is greater than or equal to 0. And I didn't really do algebra to solve this. I just know that if x cubed is greater than or equal to 0, then x has to be greater than or equal to 0. Right? Does that logically make sense to you? And if you were to graph y equals x cubed, this is the only place where the graph is above the x-axis. Which means our domain is from 0 to infinity, including 0. Range I wasn't 100% sure on until I looked at the graph, but it is from 0 to infinity also. The graph was continuous, has a local min at 0, 0. You could say increasing over the entire domain, or you could just say increasing over 0 to infinity, either one or both. There was no symmetry, which means it's not odd or not even. And I checked algebraically to see if I could make it work out, and it didn't look like it was going to. The graph is bounded below. There are no asymptotes. I told you this was going to happen in one of our examples. The left hand end behavior does not exist. So we can't say it's equal to anything because the graph doesn't do anything on the far left. So when you write your limit notation for the end behavior, that left hand end behavior, we just say it does not exist. There is no end behavior there. Would you like to? That means no solution or the empty set. Would that be appropriate here? Probably, I don't know. It does not exist to be safe. Or like you could just leave it out too. You don't need to even write anything for it because it's not, there's nothing there. This whole idea of end behavior is what's going on in the graph way, way off to the right, way, way off to the left. Well, there is no graph way, way off to the left in this one. All right, for a second one, check as far as you got anyways. Were you able to rewrite this as 2 times x to the negative second? So your power is -2, your constant, the variation is 2. Hopefully recognizing, since I have a denominator here, that denominator cannot equal to 0. So x squared is not equal to 0, which means x is not equal to 0. So our domain here would be everything except for 0. And if you chose to write that in interval notation as we practiced in chapter 1, that's fine. It would look something like this. But I'm okay with you writing double bar r except 0. ARN, you will receive 0 credit if you write ARN on a test in this class. Okay, that doesn't mean anything. I'm sorry that you were taught that. Okay, use the double bar r or interval notation. This one does have a discontinuity at x equals 0. We don't need to get really specific about what type of discontinuity it is. Just say it is a discontinuity. It would be an infinite jump, but that's not super important. It has some increasing and decreasing. This one did end up being symmetric about the y-axis. And sure enough, when we tried plugging in negative x, we got back to the original function, which means it is even. It was bounded below, had a horizontal and a vertical asymptote. Make sure for your asymptotes you're writing equations, not just numbers. And this had end behavior on the left and the right, both equal to 0. Those limits are both equal to 0. All right, so again, a lot of what we're doing right now is just practicing stuff from chapter 1. Messing around with power functions today, with the ultimate goal being on Thursday, we're going to start working with polynomials. And polynomials are just a whole bunch of power functions added together, right? Power function is just a coefficient with x and an exponent on it, right? A polynomial, just a whole bunch of those with plus signs and minus signs in between them. So that's why we're practicing this today. We're going to get into graphs of polynomials, x-intercepts, behavior of the x-axis. Does it bounce off or does it cut through the x-axis? Does that sound familiar? And behavior and all that fun stuff. So we'll get into that on Thursday. But that's what we got for today. You guys got a good chunk of time here to start on homework. Let me put that assignment up on the board for you.